and phase transitions. This particular session is a lab session. So here we will try to have introduction to OpenFOAM, and then we will try to do the hands-on training. So any existing case of the OpenFOAM we will try to run over here. So let me first give you an idea about why we are using OpenFOAM. So first point is, we all know that this course, whenever we are discussing about wetting, capillarity and phase transition, all these things are associated with fluids. And when we talk about phase transitions, then we are also talking about the heat transfer. And we know that in order to understand the dynamics of any fluid dynamics and heat transfer problem, what we typically need to do is, we need to solve the partial differential equation, which are the governing equations. Even not only for fluids, for any of the system which we need to mathematically analyze or theoretically analyze based on the physics of the problem, we first define some governing equation which typically are of the form of partial differential equations. Then either we can solve these equations theoretically, or we can employ some computational techniques to solve these equations, because theoretical solutions are limited. These are applicable only for the simple situations. So in terms of fluid flow and heat transfer, our governing equations are nothing but the mass conservation, then we have momentum equation, and if heat transfer is also involved, then additionally we need to solve the energy equation as well. Mainly we will be focusing only to the Newtonian fluids. That's why whenever we will be considering the momentum equation, particularly the deviatoric stress component in the momentum equation, that will be approximated using the Newton's law of viscosity. And another important point is, because the first example which I will be discussing, that will be purely a fluid mechanics problem. So that's why we will not be solving energy equation for that. And third important point is, I will be using the case of air and water. Water, we all know, is incompressible. Like, even we can compress the water if we increase pressures to excessively high values. But air, we know that with small changes in the pressure also we can actually compress it significantly. But the value of flow Mach number which we will be considering for our case, that will be less than 0.3. So that's why we will be doing incompressible flow analysis, because the density change of the air will be very small for the given flow conditions. Now, whenever we do solve the governing equations, because I am using some, I am taking the help of the computer. So if I am taking the help of the computer, it means I am numerically solving these governing equations. Okay. So to numerically solve fluid flow and heat transfer problem, there is one popular term which is called as CFD. And CFD is nothing but, it is called as computational FD. So FD is our fluid dynamics. So typically whenever fluid, we are taking the help of the computers to understand the problem of fluid dynamics, then we are calling it as computational fluid dynamics. Another important point you have to keep in mind, that computers does not understand how to solve partial differential equations. The only thing we can do in computer is, either we can solve, we can do the arithmetic operations, or we can compare some logical expressions where greater than size, smaller or equal to sign, that type of comparisons we can do. So it means that if we have to use the computers for solving our partial differential equations, then first we need to convert the governing equations into the form which is actually understood by the computers. So the process of converting a partial differential equation into an algebraic system of equation is something which is called as discretization. Now, when we do discretization, there are different processes. Okay, either I can employ finite difference method for doing the discretization, I can employ finite element method to perform discretization, or I can employ finite volume method to perform discretization. In most of the cases, in most of the fluid flow and heat transfer cases, though other methods can also be used, but the popular method which is implemented in most of the commercial and the open source solvers, that is finite volume method. So FVM is the mostly used in most of the commercial and the open source software. So OpenFOAM is also based on the finite volume discretization. Now, whenever we talk about any of the CFD software, there are different ways. Some of the softwares are commercial. For example, all of you know popularly about ANSYS Fluent. It's very popular. Then we know about ANSYS CFX. We know about Star CCM. We know about Console. So all these softwares are nothing but commercial softwares, licensed software. So depending upon the requirements, whether we want to use it for the academic purpose or for commercial purpose, the company will be issuing some license, and for that license they will be actually charging from us. And in order to, because the companies, what they have to do, they have to actually sell their product. So this is a product for them and they have to sell their product. So once they have to sell that, they will be making the software in such a way so that it should be user friendly. So that is the reason with most of the commercial softwares you will be finding there is a well defined interface. You have to select some option, you have to take down some menu, it will be opening some window. There is some prescribed set of options that if this thing you want to choose, then click on this button. If this thing you want to do, then click on this button. So that type of arrangement you will be having. And other issue, so this is the user friendly nature, but the other disadvantage with the commercial software is that whatever the license you have purchased, say you have purchased the license for fluid flow and heat transfer problem, and now you want to do some problem in structural dynamics, or say some problem where fluid structure interaction is required, then you may have to purchase first separate module for structures. Other important point is, many times whenever we do solve the problem, say in standard equation, I want to do small tweaking. So what happens sometimes, say I have surface tension implemented in the standard solver in certain way, but I found that the situation which I am having, there I am having surfactant available, surfactant present at the interface in the physical phenomenon. So if surfactant is present, then ultimately my value of surface tension will not be constant at entire interface. Okay, so at different portions of the interface, surface tension coefficient will be different. So ultimately, we need to now incorporate we need to modify the momentum equation in such a way so that I can incorporate the gradient of surface tension along the interface. So in that case, I need to do some modification into my governing equation. So majority of the time with commercial software, the source code of the software is not available to the users and we cannot do these type of changes. Of course, these provide some flexibility in the form of user defined functions, where for certain terms you can use the user defined functions which can assist in these situations, but we cannot do significant changes in the code because it is not available to us. So that is where actually open source solvers come into picture. So open source solvers are the ones which are mostly developed by different researchers from various research organizations across the globe, and initially they have developed these for some of their initial problems, and later on when different people started using these, then the group has become big and they have tried to do the developments for different type of problems, and once all these developments are consolidated together and put on a common platform, so that has become a popular open source solver. There are large number of open source solvers available for different type of problems, but OpenFOAM is the one whose community is actually very wide, and OpenFOAM community has come up with this software for large range of problems which are not only limited to the fluid dynamics, but nowadays this is available even in other areas such as for structural analysis, even molecular dynamics and other type of simulations are now possible using the OpenFOAM. OpenFOAM was initially started by Henry Weller. So, he was a chemical engineering student in Imperial College somewhere in I think 1988 or 1992. The first Fortran version of this solver was prepared by him for solving some fluid dynamics problem, and later on sometimes in 98 or 2000 this has officially put on some platform, and they have now this entire solver in the C++ and object oriented programming. So, what we will do over here, OpenFOAM, as I told you, that it is available for wide range of problem. For example, if you have to do a conjugate heat transfer problem, then there will be some other solver available in the OpenFOAM to do that. If you have to do some multi-phase flow problem, then there will be some other solver available. If you have to do some single phase flow simulation, for example, flow through a pipe, then there can be some other solver available in the OpenFOAM. Among all these solvers, we will try today to use the one which is called as InterFOAM. So, InterFOAM is the solver which we will try to practice in this hands-on session. What we have in this InterFOAM solver, this InterFOAM solver allows us to simultaneously study the behavior of a system which contains two fluids. So, for example, if I have fluid 1, this is my fluid 2. Now, there can be two types of occurrences in these two fluids. One could be that my fluid 1 is homogeneously mixed in fluid 2. So, that is a miscible solution. Other combination could be that the fundamental nature of the fluid 1 and fluid 2 is in such a way so that they cannot mix with each other. Okay. So, these are of immiscible nature. So, the one which we will be talking about over here, that will be actually immiscible fluids, because we are talking about the contact line interfaces. So, these will be majorly possible with the miscible fluids, where interface will be forming between two fluid layers. Now, this is my interface. So, the boundary which separates fluid 1 from fluid 2, that is actually called as interface, and basically at the interface we are having some jump in the property. In fluid 1, above the interface I will be having value of density as say rho 1, and below this boundary I will be having value of density as say rho 2, likewise viscosity and other properties. Now, typically at the macroscopic level, if we look at the interface, we typically observe that one type of molecules are in bulk of fluid 1, and in the interfacial region I will be having combination of molecules of two kinds. So, here you can see all these open circles, this is representing bulk of fluid 2, and all the filled circles are representing bulk of fluid 1, and in between I have the molecules which are actually combination of both the type. This is typically the interface. So, if we see from microscopic perspective, interface is typically having finite amount of thickness. However, whenever we look from the macroscopic perspective, then typically the length scale of this is less than 10 to power minus 6. So, it is less than even a micron. So, at the macroscopic level, we assume interface for two dimensional case to be a simple line, and for three dimensional case we consider it nothing but as a 2D surface. So, we do not take into account the diffuse interface concept. This is called as diffuse interface concept, and whenever we are not considering the thickness of the interface, we are considering it as a sharp jump of the property across the interface, that we call as sharp interface concept. So, when we will be numerically implementing it for large scale fluid flow and heat transfer problems, we will be considering a sharp interface concept. Now, another important point is, we all know from our basic understanding of fluid mechanics that for solving fluid flow, we need to solve continuity and momentum equation. Now we have two fluids. So if we have two fluids, then we have to solve continuity equation for fluid 1, momentum equation for fluid 1, and then another set of continuity and momentum equations for fluid 2. And along with that, I will be having interface. So at this interface, I need to supply some boundary conditions which will be applicable at the interface. So typically in a single phase flow, if entire pipe is filled with same type of fluid, within the domain we need not to define any type of boundary condition. Only we will be defining boundary conditions at inlet, outlet and at the solid boundaries. Whereas in case of multi-phase flow, or if two fluids are simultaneously flowing, then in the pipe I may have the portion of the tube filled with fluid 1 and portion of tube filled with fluid 2. So in addition to the boundary conditions at inlet, outlet and at the pipe wall, we may also need to define boundary conditions, how forces and momentum is being exchanged between the fluids, typically at the interface profile. So this type of approach where we separately use the momentum and continuity equation for each phases, and then we apply the boundary conditions at the interface to exchange the forces and the momentum, we call this approach as two fluid approach. And the other way could be that I have this interface. Instead of using the two fluid formulation, I may consider that I will be using single set of governing and momentum equations, but I will be using in such a way so that when I am pointing to the portion in bulk of fluid 1, I will be using the density and viscosity of fluid 1. When I am there in the fluid 2, I will be using density and viscosity of fluid 2, and typically the computational cells which are lying across the interface, there we will be defining certain way of averaging the property, and we will define some volume average property which will be representing combination of or average representative of properties of the mixture. This type of approach where we are using single set of equations and we are defining some volume average properties at the interface, that is called as single fluid or one fluid approach. When we are using the one fluid approach, but still we have interface, so our continuity and momentum equation will be remaining the same, but in addition to that, in the momentum equation, we have to add some additional force term which can account for different forces which are acting at the interface. So typically the force which is acting at the interface will be surface tension force. So we have to include in our momentum equation additionally the surface tension force in addition to the momentum equation which we are using for single phase flow problems. So this type of approach is one fluid approach, and typically the one fluid approach is implemented in interFOAM solver. This OpenFOAM is having even solver for the two fluid approach available, but mainly in this particular session we will be only focusing on the solver based on the single fluid approach. Another important point is, so maybe this part I will skip. Yeah, so now one additional point is, you can see that when flow will be happening, then can the interface stay as rigid at its original location? Interface will be keep on changing its location in the space, and also with the space and time it will be evolving. So another issue is, it may be known to us that what is the initial configuration of the interface, but whenever we will be progressing our solution with space and time, then that initial interface location has to evolve with space and time. So it means that we need to do certain arrangement with the help of which we can mark where is our interface, and then that particular property we can have some governing equation for that particular property, which will be then evolving with space and time. So we have different type of methods which are available for defining the interface. Let me briefly explain you. थिनर लाना, उससे इसको साफ कर देना, थिनर से साफ कर देना. So one important point we need to understand that, because what we need to do, we need to solve our governing equations using computers. So we need to do discretization, and discretization also I told you which type of discretization we will be using here. We will be using finite volume discretization. So whenever we use the finite volume discretization, what we do, we divide the domain into large number of volumes of finite size. So say you can see over here all these small rectangles, these are nothing but number of volumes of finite size. And typically in finite volume method we can go for either vertex. We will be particularly going in FBM method for the centroid approach, where at the centroid of all these finite volumes we will be defining our node points. What is the meaning of node points? It means these are the locations which are actually containing the values of all the field variables. And what are the field variables we have? When we will be solving continuity and momentum equation, we will be having velocity field. So UVW, 3 components of the velocity. We will be having pressure P, and along with that we will be having 2 properties, density and viscosity. Okay, and when we are doing the multi-phase flow situation, we have to also additionally solve the surface tension force. So sigma will also be coming. So over my numerical grid, in the different cells I need to specify that what is the value of all these field variables, and typically at time t is equal to 0, when we define the initial configuration of the system, we specify the value of all these properties. Now let us assume that this is my interface. So if this is my interface, everywhere above this I have fluid 1 and below this I have fluid 2. So typically what we can do, over here I will be mainly using the VOF method. VOF method is called as volume of fluid method. So interform solver is based on the volume of fluid method for defining interface and evolving interface with space and time. There are large number of methods available. I am not going to discuss that. Over here I will be only talking about the volume of fluid method. What we typically do in volume of fluid method, we define one value which is called as volume fraction, and the value of volume fraction is nothing but volume of the primary fluid in the cell divided by total volume of the cell. Now out of these two phases, one we will be defining as the primary phase and other we will be considering as the secondary phase. Now you can see the cells which are completely filled with the primary phase, their volume fraction will be 1, and the cells which are not having primary fluid, their volume fraction will be 0, and the cells which are containing the interface, their volume fraction will be somewhere in between 0 and 1, depending upon the amount of primary phase present in that. For example, these cells typically can have volume fraction close to 0.4, 0.5, maybe 0.4 again, and some of the cells may have volume fraction as 0.1 or even say, depending upon the volume, 0.7 or so. Now, what I have got that where I am having phase 1 present, there where volume fraction is 1, there only primary fluid is present, fluid 1 is present, where volume fraction is 0, there secondary fluid is present, and the cell which contains the interface, their value of volume fraction will be in between 0 and 1. So, through this way, we are able to calculate the value of volume fraction, and this configuration of the interface was known to me because I have initialized this interface at time t equal to 0. So, when I am using the word initialized, it means I am defining it at t equal to 0. But what I need to do now, this interface will not stay at its location. Depending upon the velocity and the pressure field around it, it will be actually traveling with space and time. So, once this interface is moving, I need to define some equation which can actually transfer this volume fraction field among different cells. So, for that purpose, what we do, we define one equation which will be an addition to the volume fraction, which will be an addition to the momentum and continuity equation, and that particular equation is called as advection of volume fraction. So, in addition to that, I will be having, in addition to continuity and momentum equation, I will be having one equation for advection of volume fraction. Okay, so can you tell me how volume fraction will be advecting? So, typically, if you have interface, okay, if I calculate the component of velocity which is normal to the interface, if I calculate the component of the velocity which is aligned normal to the interface, so that normal component will be parallelly shifting the interface to some new location. Is this point clear? So, if I can calculate the velocity in the direction normal to the interface, then that normal component of interface will be simply shifting this entire line to some new position, and how much jump will be taking from this point to this point, it will be actually decided by what is the time difference in between these two instants. Is this point clear? So, it means that we have to develop some mathematical equation which can first calculate the velocity normal to the interface, and after that, that can advect that value of volume fraction field with velocity. So, it means that if I define my volume fraction with parameter alpha, I can say that the rate of change of alpha with time will be dependent upon velocity field into gradient of the alpha. So, dot product of velocity field with gradient of alpha, and ultimately, because the value of alpha is conserved in the system. So, whatever fluid 1 you have, whatever fluid 2 you have, your interface can deform, but the amount of total volume fraction within the system should remain conserved. So, ultimately, this variation should be equal to 0. Is this point clear? So, first term is representing the rate of change of alpha with time, second term is representing how alpha is evolving with the velocity field. One important point you have to now understand from the basic physics, I told you that I need to calculate the normal component of the velocity, and that will be telling me how interface will be actually moving. So, I am using over here the gradient operator on field alpha. What is field alpha? Field alpha is 0 here, 1 here. Okay. So, in bulk of the fluid 1, fluid 2, value of gradient alpha will be 0. In bulk of fluid 2, gradient of alpha will be again 0. First point is gradient of alpha will be only applicable at the interfacial cells. Second important point, whenever we mathematically apply gradient operator on a scalar field, then the gradient of a scalar field always define the direction normal to the constant contour of that scalar quantity. Is this point clear? So, it means that the gradient of alpha is defining me the normal direction. So, that is why I am using this V vector dot gradient of alpha equal to 0. So, this equation is typically my advection of volume fraction field. This equation is for advection of volume fraction field. Yes.
So, this equation is coming from general transport equation.
Yes.
So, why we are neglecting the diffusion and
yes.
Source term?
Yes. So, first point is that what is this? Alpha is a scalar quantity. So, one of his question is, we typically have scalar transport equation which is given as del of rho phi by del t plus advection term, that will be divergence of rho v vector phi plus equal to diffusion term, which will be divergence of gamma times gradient of phi plus some source term, which represents temporal term, advection term, diffusion term and the source term. So, typically if you talk about field like temperature, so temperature is a property. If you have property, if you have the difference of temperature between two locations, then one additional transport property, thermal conductivity, comes into play, which leads to diffusion of heat from high temperature to low temperature. Okay. So, then this term becomes active. If in the domain you are say heating some portion of the domain, so that particular portion of the domain will be continuously getting the heat, so that will be acting as a source term. But over here, whenever I am talking about the volume fraction field, it is not any fundamental property, rather it is a mathematical operator which we have defined just to take the advantage so that we can specify the value of the interface. So, it means that with this mathematical operator, because it is not a fundamental property, there is no diffusion associated unless or until you consider that between the phases you have concentration. Is this point clear? And there is no generation of source. So, this source term will be activated if you talk about boiling and condensation phenomenon. In case of boiling heat transfer, what will be happening? Liquid mass will be changing into the vapor mass. So, then some volume fraction of liquid has to be converted into vapor. Then this source term should be activated. But in case you are not considering any phase change, the source term will also be equal to 0. Is this one clear? Okay. This point is clear. Then let us discuss one more point. So, first point is we are dealing with incompressible two-phase flows, but we are solving these using the one fluid approach. So, if we are solving these using one fluid approach, we have to solve the continuity equation for incompressible flow, which is divergence of velocity vector is equal to 0. Yes, yes.
Basically, this would mean that if I take a differential volume at the volume fraction within that cell should not change.
Yes, yes,
As I follow the material part.
yes. Overall, yes. If you follow material particle, it should not change. Yes.
But physically, how do you get this principle? Like, this is the mathematical sort of translation of this equation in the physical words. But from physical principles, how do you get like
Because alpha is not a physical quantity, it is simply a mathematical tool, mathematical quantity which is introduced to define the interface.
that is fine, but eventually we are getting that equation.
Yes, yes,
We are solving all our system based upon that equation also.
yes, yes,
Now, so that equation is basically saying that if I consider a differential volume, the alpha or in that alpha of let's say fluid one should not change with time.
yes, yes. No, that it is not saying ultimately. So, whenever you will be discretizing it, what will be happening? Say, I'll give you one simple example. Because the numerical solution of this equation is not identical to one which we simply do for single phase flow. So, here what will be happening, say I have a one dimensional grid. This is my one dimensional grid, and in this one dimensional grid let me consider that this is completely filled with fluid 1, this is completely filled with fluid 2, and this is partially filled with fluid, and say I have over here my volume fraction close to 0.2 or 0.3. Now if this is a one dimensional flow, so in one dimensional flow my velocity field will be approaching in rightward direction. When say my time step is in such a way so that in single time step solution is jumping from this point to this point. When I will be solving this particular advection term, I need to calculate how much flux will be transporting from this boundary to the next boundary. While I am defining the flux calculation for this, I have to define in such a way so that till the time interface is reaching this boundary, value of flux of the reference phase or flux of alpha should be 0. Once it is crossing the boundary, then only there should be some positive flux of this quantity. So ultimately what I am saying is, I am not saying that within a single cell this value is conserved. As a whole it is conserved for the entire domain, but within a single cell when I need to solve this equation, in addition to simply mathematically applying the advection operator, for flux change I also need to take the help of geometry of the interface in order to decide how volume will be transferring across the boundary of different cells. So maybe partially I could able to answer. Okay, okay. So one is continuity equation which I have already written. Divergence of v vector is equal to 0. Other is momentum equation. So in our momentum equation we will be having del rho v vector by del t plus divergence of rho v vector equal to minus gradient of p plus mu times del square of v vector. This is the single phase momentum equation. Now I need to put additional term which is surface tension force. We have seen in the previous lecture surface tension force is nothing but sigma times mean curvature of the interface, and when I am writing this sigma times mean curvature of the interface, now this equation is written on per unit volume basis. If it is written on per unit volume basis, what will be happening? When I will be numerically integrating it over the entire volume, so this force, this term will also be calculated for the complete volume. But in actual, this is nothing but a surface force which is only acting at the interface. So it should be calculated only for the cells which are containing the interface. So to implement that part, we will be putting one additional gradient of alpha operator over here, so that the value of this operator is becoming 0 for bulk of the fluids, and this force is coming into picture only for the cells which are containing the interface. Now, then this advection equation which I have already written. In addition to this, we also need to define the properties for the cells which are containing mixture. So, for that, typically what we do, we simply define mixture property as value of alpha into rho 1 plus 1 minus alpha into rho 2. So, simply based on the volumetric averaging. And mu we define alpha into mu 1 plus 1 minus alpha into mu 2. Is this point clear? So, maybe now we have some idea about the governing equations which we are going to actually solve, which we are going to solve in the interform solver. Is this point clear? Now, after this, after the governing equations, you have to also understand one point, that whenever this volume fraction advection equation will be changing the volume fraction field, after the volume fraction field, in each and every cell, new value of the volume fraction will be coming up. What we need to do with that? Once the new value of the volume fraction has come, if I want to know that what is the shape of my interface at some intermediate cell, then based on the volume of the volume fraction field, I need to reconstruct the interface profile. So, it means I need to do some geometric operation with the help of which in the next time step I can define that if this is my value of volume fraction, then what will be the shape of the interface. For defining the shape of the interface, two simple approaches are used. There are many, but say I will give you very brief idea about two approaches. One is called as slick, which is called simple line interface calculation, and another is plick, which is piecewise linear interface calculation. So, what is typically done in slick and plick? Here you can see in slick what we are doing, we are defining the horizontal and vertical lines in a grid cell which is containing the partial value of the volume fraction. Okay. And so, it means that in reality your interface is a smooth curve, but whenever geometrically we will be reconstructing, it will not be a smooth curve. It will be having some broken lines between the different grid cells. And if our grid size is small enough, then actually we can get good amount of approximation of the actual profile of the interface. So, the approach in which we define interface by just using the horizontal and vertical lines for defining interface, that approach is called as slick. Now, one important question can come to your mind, say if value of volume fraction is 0.2, then you have to decide this vertical line in such a way so that it is covering only the 20% area of this particular cell. In the similar way, horizontal line should also be placed like this. But then it may also so happen that whether to place this line here or horizontal line on bottom or top. So, typically what is done, the normals to the volume fraction field are calculated in the neighboring cells, and depending upon all the neighboring normal directions, it is decided that the line which is matching closest to the surrounding cells normals, typically these line configurations are actually used. Again, there are large number of methods, we will not be able to discuss here. And in case of plick, what is considered, rather than using a horizontal line, you can consider an inclined line which is having slope, and this slope can be easily calculated from the direction of the normal. If you know the normal direction of normal to the interface, you can easily calculate the value of slope of this line. And this line, then where to place, of course, intercept of the line can be again estimated based on area conservation. So this type of approximation is called as piecewise linear interpolation. And these interface reconstructions, slick and plick, these are not only required for intermediately visualizing the flow, but in addition these are also required because whenever I will be solving the advection of color function equation across the common boundaries of the adjacent cells, I need to define how much volume of reference phase is crossing the boundary. So for accurately estimating that volume which is crossing the boundary, we take the advantage of geometry of the interface also. So basically the flux calculations are done by taking advantage from geometric reconstruction of the interface. So it means that in volume of fluid method, in each time step we do two additional things. One is we do the interface reconstruction based on the data of the volume fraction, and then in the next step we advect the interface, we advect the volume fraction field to the cells in the next time step, and again then we do the reconstruction. Is this point clear? So with this theoretical background, let's now try to see the files of the interFOAM solver. So maybe in your computers also these files are already loaded, so you can also open and check the files. इसमें कहाँ पे डाली है फाइल्स, कौन से फोल्डर में है वो बता दो एक बार. डॉक्यूमेंट्स में जाके. Home folder, within the home you will be finding there is a folder named OpenFOAM. So there is a folder OpenFOAM in your computer, all of you have got it. Now within the OpenFOAM folder you will be finding there are two folders, OpenFOAM 7 and third party 7. So this is the 7th version OpenFOAM 7.0, so that's why 7 is written over here. So typically the different advancements are taking place, and presently I think recently even OpenFOAM 11 is also launched. So third party, so OpenFOAM folder typically contains all the files which are required for operating the basic source code of the OpenFOAM and script required for running the different problems. And third party software, because we also need to do visualization, and sometimes these also use the some dependent libraries of other software. So all these third party softwares which are required, for example for visualization we will be using ParaView, so all these are stored in this third party file. Now if you go to OpenFOAM folder, inside this typically 2-3 folders are important. One folder is SRC, and in this SRC you can see a large number of folders are there. So basically the SRC folder, if you open any of the model, you will be finding inside that this contains, SRC folder typically contains the entire source code of the different solvers, and this is structured in depending upon their nature of the solver. And then we have another solver which typically will be of interest to us at the moment, that is tutorials solver. So if we go to tutorial solver, you will be finding that basic, so basically basic contains simple equations where you can solve partial differential equations by applying certain boundary conditions. Then you have combustion solver, compressible solver, DNS solvers, electromagnetic, even some financial things can also be done using OpenFOAM, heat transfer, incompressible. So large number of solvers are there. Even stress analysis is also there, and even other than that, some of the individual research groups, they have not incorporated their versions into the main version, but people have also developed some molecular dynamics, fire dynamics solvers with the OpenFOAM. Now, in this, we will be going to multi-phase. We will be going to multi-phase solver. When we go to multi-phase solver, within the multi-phase solver, again we have large number of solvers there. Cavity form, compressible interform, compressible multi-phase interform. So we will be simply using, at moment, we will be using the interform solver. So now I will be clicking on interform solver. Now within the interform also there are three different: laminar, LES, RAS. So whenever we will be working with fluids, if our Reynolds numbers are high, then the flow can be turbulent. And for resolving turbulent flow, we have to apply different models such as Rains based averaging or large eddy simulations approach. So, but over here we will be mainly focusing on the laminar flow situations. So, I will be then entering into laminar folder. In the laminar folder, again there are large number of tutorial cases given. Over here, the one which we will be referring to is the dam break problem. I will be clicking on dam break, then again I am getting dam break folder. Let us click again, and if I enter into the dam break folder, I will be finding this zero, constant and system folders. So these are three important folders to run a case file of OpenFOAM. Zero, constant and system. So you can understand that zero folder is the one, its name itself is specifying something. So zero folder is one where we can do initialization of various field variables, and where we can also apply the boundary conditions. So typically in the zero folder, the files which are stored, these contain data with reference to initialization and the boundary conditions. Then we have constant folder. So typically the constant folder containing the data which is actually, which will be remaining kind of fixed during the simulation. So what are the quantities typically will be remaining fixed during the simulation? So we need to specify over here all the thermophysical properties and their associated models. And then we have the system folder, which will be typically containing the files where we need to apply certain schemes. So whenever we do CFD, it's not like that randomly something will be actually happening. In CFD, basically the approach is, whenever we convert all these governing equations into algebraic set of equations, then to solve the algebraic equations, we need to apply specific schemes. For example, for solving convective part, we apply upwind schemes. For solving the diffusive part, we apply central difference schemes. So all these schemes, which type of method is to be chosen for what type of interpolation, that everything we need to specify. And we also need to set the control parameters. What should be the critical value of the residuals? What should be time step for transient simulation? After what interval we should store data? Where we should save data? So all these details will be actually available with the system folder. So if you typically see in 0 folder, you have how many files? 3 files. One is alpha.water. Alpha.water means primary, alpha is volume fraction, and dot water means water we are considering as the primary phase. Okay. Then we have P underscore RGH. So this is a pressure field. Then we have U as velocity vector. If you go to constant, you have 3 folders. One is G, which is containing the data of gravity. Then you have each and every file I will be browsing. Now I am just telling you the sequence of files. Then transport properties and turbulence properties. And if I go to system folder, there I will be getting block mess, which will be for defining the mess. I will be having control dict for defining control parameters, decompose pair dict if I need to do a parallel simulation and I need to decompose the domain into multiple parts so that I can run it on a multiple cores, then I will be using this. And then I have FV schemes, finite volume schemes. This will be containing the information about all the CFD schemes which we will be using for solving. And FV solution, it will be containing the information about the solution methods. Once you have algebraic set of equations, we will be getting the linear system of algebraic equations. That system of equation we need to actually solve. So whether we want to go for the direct methods, whether we want to go for iterative method, what under relaxation or over relaxation factors we want to choose, that information we will be giving in FV solution. And then another is the set field. So set field is an utility which is typically employed when we need to initialize some specific value of the field variable to some specific portion of the domain. For that purpose, we will be using the set field. Okay, so over here the problem is dam break. So basically, in this particular example, the physical situation is we have some box and this box is having some obstruction here, and in this box here I have initialized a water column. So this is my water column and rest everywhere I have air. Now this is impermeable wall, this is impermeable wall, entire bottom is impermeable wall, and top is just opening of a tank from where things can go out and can come inside. Now typically if you take a column of few centimeters or few meters height, what will be happening? Because of the gravitational field, it will be splashing down. So that is what we want to see over here. So our idea is we will be initializing a water column, then how this water column traverses with space and time, that we want to simulate. Now what we need to do, whenever we do any simulation, we need to first define the geometry and the mesh. After we define geometry and mesh, then only we can proceed for the solution. So let me define the geometry. Of course, you can use any other softwares for defining the geometry and mesh. OpenFOAM allows the flexibility of importing the files from other softwares, but we will try to use its own script, how it defines actually the geometry. So, another important point is whenever we do simulations, either we can do axisymmetric simulations, we can do two-dimensional planar symmetry simulations, or we can do three-dimensional simulations depending upon the nature of the problem. Of course, this situation is not fitting axisymmetry. It may enter into the three-dimensional nature, but 3D simulation will be taking significant amount of time. So, at present we will be doing this simulation in a two-dimensional manner. Okay. So, 2D simulation I will be doing. So, in general, whenever we define the domain using block mesh, we define hexahedra something like this, a three-dimensional structure. But whenever I will be using for simulation for 2D, then also in OpenFOAM, because the solver has to make consistency with the files, so they define hexahedra only. The only thing is done when you will be defining your mesh, we will be defining only the mesh along the directions, two directions. In third direction, we will not be defining any computational cell, any number of divisions, the direction which we want to keep, where we do not want to solve the solution. So, this is just for the purpose of using the same file for 3D as well as for 2D simulation. Now, if you have this type of geometry and you can only use the boxes to define the geometry, what I need to do? I need to split this geometry in such a way so that this entire structure can be made by using different rectangular boxes. Okay. So, what I will do, I will split it from here, and this will be my box 1, box 2, I will also split it like this, this will be box 3, then split it like this, which can be box 4 and box 5. Okay. So, if I split it into 5 boxes, then I can actually prepare this entire geometry by just assembling all the boxes. So, that is what we will be doing now. So, how to do it? Let us see in this block mesh dict. Okay, so if you open your block mesh dict file, it will be looking something like this. Now you see in the top, one term is written convert to meters. So typically this value is like we can define over here the vertices of all the points in any system, and if later on I want to finally use meters as my system, then what I can do? I can apply the multiplying factor over here. For example, if I want to define all my geometric parameters in millimeter, so then I will be simply using the 10, 20, 30 as my say vertices. But ultimately in actual system, the things should process in the same set of system of equations, because ultimately I will be defining all my other properties as well. So, say if I am defining my properties in SI units, then my geometry should also be converted into SI units. So, for converting the geometry for any given dimension of vertices to the SI system, we will be using this particular multiplication factor. Is this point clear? After this, it is written vertices. So, after that we need to define the vertices, means in a three-dimensional system XYZ locations of different points. So, you have to understand that if I have to make all the 5 boxes, can you tell me how many corner points I will be having? You can start from this. Say it is my 0, I am giving say 0 index to this one, then 0, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now what I need to do, 11 means overall 12 because I started from 0. So I need 12 vertices for defining only the front portion. But as I told you that we need to define a 3D volume. Okay. So in order to define a 3D volume, there should be some backward face of this entire portion. So the backward face will be having 12 more points. So in total, how many vertices I need to define? 24 vertices. So if you see in this vertices column, there are actually how many entries? You count all these are nothing but 24 entries. Okay. When these 24 entries are coming up, you have to keep in mind the sequence. Always the first entry comes as 0th location, next entry comes as 1, 2, 3, 4. Now, depending upon the location of this, if I start it from 0, in the further portion of the script, I can call any of the entry. But sequence should be known to me. Okay, is this one clear? So first will be from 0 and all other in whatever sequence you are writing, it will be following 1, 2, 3, 4 and later on when you will be using, you can use 4 first and 0 later, but you should know that which point is 4th and which point is 0th. Is this point clear? Now let's see, from this itself we will try to remap the geometry. So what is my point 1? What is my point 1? 0, 0, 0. So say this is my 0th location. What is next point? 2, 0, 0. So in x direction, let me define over here. This is x, this is y, this is z. So in x direction, I will be moving how many points? 2 points and rest is 0, 0. Then after this, 2.16 somewhere over here. Then after this, 4, 0, 0 somewhere over this. So this is my 4 points are defined. What is the next point? 0, 0.32 and then in y direction I am moving. So it means somewhere over here, my 4th point. Likewise, if you see 5th point, 6th point and 7th point. 7 points are done. Then what else? 0, 0, 0, 4, 0. Okay. So this one 0, 4, 0. So y direction I will be moving 4 points. This one. So this is my 8th point. Likewise, if you see, this will be 9th, 10th and 11th. Now can you tell me what is the 12th point? 0.1. 0.1. So right now we were in which plane? In z direction we were in the same plane, but now we have started shifting towards the z direction. So it means I am shifting in the z direction. So somewhere over here is my 12th point. Now in the same sequence, I will be slightly shifting towards the back side and this will be 13th, this will be 14th, 15th and then likewise here I will be having 16, 17, 18 and 19 and then you can see the 20, 21. I have defined all the 23 vertices. All are clear? You can also see that in z direction, the thickness defined is very less because in that direction we need not to solve the equation. So this is just a dummy direction for us. Now After we defined all the vertices, next part is what? Blocks. What we define in blocks? First hex. First hex is containing how many points? 0, 1, 5, 4. Let me join from 0 to 1. This is my 0, 1. Then it is joining 5. Then it is joining 4. It cannot be open ended. So it will be again joining to 0. And what are the other 4? 12, 13, 17, 16. This is 12, 13, 17, 16. And ultimately, if I join these sides, what it has become? It has become a box. The only thing you need to keep in mind, instead of starting from 0, 1, 5, 4, you can start even from 1, 5, 4, 0. But the thing which you need to keep in mind is, if you are starting from 0, then the previous should also start from the same point behind this and in the same sequence. Okay, so that thing you need to maintain for defining a box. That I will discuss. That will be required for faces, not for this. Here anything you can, even you can go for clockwise or counterclockwise as per your wish. Then let's first only define the boxes. What is these remaining part, remaining commands? Let's not discuss this at the moment. Now what is next? 2376. 23. What should be? Now sequence should be known to you. What should be the next 4 points? Box 2 is defined. Okay. You can go to box 3, 4, 5, 9, 8. 4, 5, 4, 5, 9, 8. What should be the next? 16, 17, 21, 20. Box 3. What next? 5, 6, 10, 10. Oh, sorry, this is 10, not this one. What should be the sequence? Next? 17, 18. Next box? 11, 10, 19, 23. I have got the entire domain. All the boxes I have got. Now what I need to do, this is my geometry is done, I need to define the meshes. When I need to define the meshes, I need to tell that how many number of elements in each direction. So of course there can be different ways. We are using over here simple grading. Simple grading is used for 3 type of things. One is to simply define the uniformly spaced number of divisions. Other is, one is for simply defining number of divisions, uniformly spaced number of divisions. Second is, if you want to give preference to some direction, that you specified number of divisions, along with that you have also defined ratio of smallest cell to the largest cell. Accordingly it will do grading. Finest will be at one edge, largest will be at the other edge, and there will be some grading. So sometimes it may so happen that interface is not participating with all the cells, it is remaining in some specific locations. Then what you can do, you can take the advantage of grading, that you will be giving finer meshes to the cells which are containing interfaces and little bit coarser mesh to the other remaining portions of the domain. So for that type of grading, that we can also do using the simple grading command, and even the reverse way grading can also be done. So when in simple grading I am everywhere writing 1 1 1, it means it will be uniformly placing the values. But if I say that in x direction I wrote 0.1, so if it is doing 19 divisions in x direction, what it will do, the left face it will make size 1/10th of the largest cell which is present on the other side, and accordingly it will be gradually adjusting the number of grids. But if I give the ratio reverse, say if I write here instead of 0.1 as 10, then the left face size will be largest, which will be 10 times to the size of the right cell. Okay, and of course gradually it will be grading all the remaining cells. Yes, so after defining geometry, we are defining that how many number of divisions, what grid we want to use. Yes, this is fixed Eulerian grid, and if we want, we can also use the dynamic grid. So that will be.
Because the interface will be moving, water will be suddenly collapsing. So, would we not need to
Find.
make separate final?
Yes. So typically one thing we can do is either we can make the entire simulation domain fine, which will be of course costly. So one thing which we can do is we can use the adaptive mesh refinement with the dynamic mesh, where wherever interface is traveling, these cells we will be making finer and remaining cells we will be making coarser. So that it is there. For 3-dimensional and 2D simulations, for 3D simulations it can be done, not for axisymmetric. So for simple grading, I have written everywhere 1 1 1. It means my number of divisions I am keeping uniform. Then the first one is 23 8 1. What it means? From 0 to 1, this particular face I am dividing into 23 small cells, and in the vertical direction I am defining it in 8 cells. Next is 19 8 1. So from this point to this point I am using 19, and here I am using 8. What is the next one is 23 42 1. Now you have to keep one thing in mind. If in this box I have used 23, then in the next box also I need to use 23, because whenever fluxes will be transferring from one cell to another cell, the connections should be pointwise, then only correct fluxes will be transferred. So in x direction for this cell, I need to specify 23 only. So if I specify 23, then all these points will be further connected. And then I am having 42. So likewise I will be doing 42 grids. After this I am having 4, 42 and 1. So it means in x direction I am using only the 4 divisions for this, but in y direction I need to do now take 42 only to make consistency. So this will be 42. After that 19, 42, 1. So of course here I need to do 19 and here I need to do 42. I am constrained. So if I am using any type of grading, then whatever the grading I am using in the bottom cell for x direction, in the top cell I also need to do the same grading. Is this one clear? Moreover, this portion can also further be specified, that in how much fraction of the edge I need to do what type of grading. That can also be further done. Maybe we will not discuss here. Okay, after this, after defining blocks, we have edges, and in case I need to define any curved edges between the points, then I need to use this option. If my all the edges are straight, then by default these will be constructed. I need not to define anything over here. After this I have one important point, that is boundary, because later on in my simulation, I need to tell that at different portions of the geometry, what are the boundary conditions. So, to define the boundary conditions, I must specify in the mesh or geometry itself that what faces will be subjected to what type of boundary condition. For that purpose, we are using this boundary type, and within the boundary type, what I will be doing now, I will be giving names to different boundaries. So, first name I have given left wall. So, in left, you can see I have defined two boxes. So, one is this face, other is this face. So, these two faces now will be becoming my left boundary. Whenever we define these faces, here we need to be very specific about the direction in which we are defining the vertices. Why? Because ultimately, if I specify a vector quantity, then vector quantity is having some direction along with the magnitude. So, then in our geometry, the outward normal direction should be defined based on the orientation of the geometry, so that it can accordingly map to the velocity value specified in the boundary condition. So, that is why here when we are defining boundary, we need to now judicially specify the sequence of vertices. So, first is written 0, 12, 16, 4. So, here you can see 0, 12, 16, 4. In which direction I am moving? 0, 12, 16, 4. Okay. So, I am moving such that my thumb is pointing in the inward direction. Okay. Then I have 14, 4, 16, 28. 4, 16, 28 again in the inward thumb pointed direction. Okay. So, when we do so, we need to keep in mind that it is not necessary that if this is started from 0, this should be also started from 4. You can use other point for defining the next boundary, but the only thing is direction in which you are defining, that has to be kept fixed. After that, right wall, if you see, okay, after defining the vertices, you know what is the type of this boundary. So, typically the type of boundary is specified either as wall or patch or empty or wedge. So, typically 4 different types are specified. If you want to define a solid impermeable boundary, then the type will always be a wall, solid impermeable boundary. If you want to define a permeable boundary, for example, your inlet to the flow, where you need to define the value of velocity, then type has to be always patch, sorry, PATCH. So, it has to be always a patch. If you are doing a two-dimensional simulation, so when I am doing two-dimensional simulation, there will be some boundaries along which I am not solving the flow. So, these particular boundaries I need to specify as type empty. For example, all the front and back boundaries for this simulation we need to specify as empty. Then, other than this, wedge will be, we will be specifying when we will be talking about the axis symmetric simulations. So, what is the left wall? It is having type wall. What is right wall? 7, 19, 7, 19, 15, 3. So, again you can see 7, 19, 15, 3. The direction is such that thumb is pointing inward. Okay. And this is also wall. So, this and this face has come as top and bottom. Now, after this, what we have? We have lower wall. So, if you see, lower wall is having how many faces? One is this, second, third, fourth, fifth. 5 faces lower wall is having. So, I need to specify the coordinates of all these faces, for example, 0, 1, So if I take 0, 1, then where my thumb will be pointing outward, I cannot take this. I need to take 1, 17, is this 17? No, 1, 13, 12 and 0. So if I take 1, 13, 12, 0, again I am pointing in inward direction. So here you can see, yeah, so 0, 1, 13, 12. So likewise I have defined all the bottom, and this also again to be a solid boundary. So if it is to be a solid boundary, type I need to specify as wall. Okay, lower wall is done. What is left? Top. In the top, 1, 2, 3. 3 I need to define. Okay, and what is this? First one they have taken 8, 20. So 8, 20, sorry, 8, 20, 21 and 9. So this way, again the thumb is pointing inward. Likewise all are defined, but important point, because when I specified the geometry, I told that top, through top something can go out and something can come in. So this is not a solid wall, but it's a permeable boundary through which material can come inside and material can go outside. So I need to define its type as nothing but patch. So instead of wall, I will be defining it as patch. Okay, so that is done. Now I have defined all the faces which are exposed to the surroundings. Okay, so it means all the boundaries I have defined. In between the boxes, I do have some common boundaries. If these common boundaries are to be given some special task, for example, if I need to make it as a solid or something else, then I can use the option of merge patch pairs to define the patch pairs and specify what task they need to do. If these are just going to serve as the part of the internal domain, then I will not be doing anything with this. So at present, because this everything will be part of the internal domain, so I am not bothering this. Okay, after this what you can do, we have defined the entire mess, we have named all the boundaries. We can close this file. After closing the file, you can come back to the original folder. Please come back to the original folder which contains 0, constant and system. And now you right click in this main folder and click on open in terminal. Is this point clear? So what you need to do, you have just done right click and open in terminal. You opened the terminal. Why doing right click? It is actually coming into the same folder only. Now we need to tell that it may so happen that our system may have multiple versions of the OpenFOAM. So we need to tell our system that which one to use for this case. So for that purpose, we will be using command OF7. So in small, we will be writing OF, and then we will be writing in number 7 and press enter. So my system will be coming to know that I am operating with OpenFOAM 7. Is this point clear? All have done this. Next, what I need to do, I need to write in the terminal block mess BLOCK in small, capital M and ESH again small. BLOCK, block in small letters, M in capital letters and ESH. All have written. Press enter. Is it doing something in the terminal? So whatever the numbers we specified, based on these numbers, it has done something in the terminal. Is this point clear? So all have done this. Now you can see on terminal some data is actually printed. For example, from the top you can see that it is defining how many number of internal faces are there, what are the number of boundary faces, what are the number of defined boundary faces. Then if you go down, it is defining patches. what are the patches? Okay, patch means left wall, right wall, lower wall, atmosphere, and then all the remaining phases. Remember this point. After defining atmosphere, in that file we did not define front and back, because front and back ultimately whatever the remaining faces are there, we simply call these as default faces, and we will be specifying the empty type boundary conditions to default faces in the 0 folder. Is this point clear? So front and back, which we have not defined, these are coming as default phases. Now after this, run the command check check and then capital MESH. Next command we can run as check mesh command. CHECK capital MESH. So are you able to run this command? If you run this command, you will be finding that some feature of mesh are actually coming. How many prism, pyramids, hexahedra are there? So ours is a symmetrical structure, so all are nothing but hexahedra. Then it is written that how many faces and points are participating in our patches, and at the end you can see that there is some skewness value written. Skewness, orthogonality, what is the minimum volume, maximum cell volume, all the parameters are actually specified. So all these are actually related to the quality of the mesh. Whenever we work with the fluid dynamic simulations, we need to actually calculate the fluxes of momentum, fluxes of reference phase, which will be crossing across the volumes. If our cells are extremely distorted, we will not be able to make correct approximation of the fluxes. That's why the quality of the mesh should be in the reasonable limit. In the blocks, this word was written HEX, hex. Hex was written, and after the hex, then we did all the uniform gradings parallel to the sides. Okay, after the check max, what you can do, you can type command paraform, PARAFO. टच करना पड़ेगा. Paraform space you can write command paraform space hyphen PARA and F will be capital, FOAM, OAM will be small, hyphen touch, TOUCH. So what you need to write is PARAFOAM hyphen touch. Have you run this command? After this, once you entered and it is successfully run, then you need to write command paraview, PARAVIEW. V small tha, capital tha. Small. So in paraview everything will be small. PARAVIEW. So paraview you have run. Now if you go into this, you have to go to file. In paraview window you have to click on file. In the file menu, click on open option. In the open option, you have to select, below there is file type. Below there is file type. Please select all files. In file type, select all files. All of you have selected all files. You will be finding one file named dambrake.openform. Is there a file dambrake.openform? Click on this and open this file. After opening this file, you will be getting again a window. In this window, you need to select OpenFOAM Reader. After opening this file, you will be getting a window. In this window, please select OpenFOAM Reader. All of you have opened it? TAs, please help those who are not getting. यहाँ पे जाके all files. ये all files. ठीक है, जिनमें नहीं है उनको बस बोलो दूसरों से लिखना. Okay, so have you gone to OpenFOAM Reader? अभी नीड थी एक्चुअली इसकी, ये रिकॉर्ड हो पर वो टेलीकास्ट नहीं हो रहा है ना यहाँ पे सर. अच्छा वो कोड. हाँ हाँ
इसमें HTML दोनों खोल देते हैं. इसका HTML उधर लगा देते हैं और इसमें तो DP को HTML भी होगा ना, उसके लिए LED के लिए लगा हुआ है HTML.
ठीक है, अभी रहने लो फिर अभी. So if you click on, after you click OpenFOAM Reader, then you will be getting this apply option in green color. So you can click on apply option. If you click apply option, you will be finding whatever the geometry you specified, it is there. Can you see your geometry what we specified? All of you are able to see the geometry, please. After this, in the top, there is one option surface. If you click on option surface with edges, if you click on option surface with edges, you can see what is the type of grid structure you are having. The type of grid structure you are having. Is this point clear? You can see in the left side one, if you little bit scroll, you will be finding one option written mesh regions. You are finding one option mesh regions. Are you able to find mesh regions? In the mesh regions, if you see now, internal mesh is actually checked. If you click on all other faces, you can see these faces will be highlighted, which are your boundary patches, just to check whether your faces are correctly specified or not. So one by one, you can click on all the faces, for example, wall, patch, etc. And if you click on apply with different color, all the faces will be actually specified. हाँ, इंटरनल अभी ऑफ किया. अच्छा अभी हुआ नहीं. You have to switch off the internal mesh, switch off internal mesh and click on all other faces, then click on apply. So you will be finding all your patches will be actually shown, which we have defined. इनको देखना जरा दीपक सचान जी को.
इसी नहीं और कुछ नहीं, ये बस चेकिंग करने के लिए क्या कितना क्या गलत
इंटरनल को ऑफ कर दो, हो गया। इश्यू
some file is not uploaded.
Oh, maybe installation is not done properly. So you can join here. Okay, so all are able to do this. So we can now close ParaView. Let's try other things. What we need to do now after geometry, we need to specify the boundary condition. We need to specify. So let's go to boundary conditions. Where we get our boundary conditions? All of you, where we get our boundary conditions, I already told you. We get boundary conditions in 0 folder. Okay. So let's go to 0 folder. Let's go to 0 folder. In the 0 folder, let me first open alphawater.org. Have you opened alphawater.org? All of you have opened? Okay, so let's see. We have in the top one line where dimensions is written and then it is having 7 zeros. So basically these are representing these 7 fundamental dimensions. For example, for length we have meter, okay, dimension of length, dimension of mass, length, time, temperature, charge. So all the 7 fundamental dimensions are given over here. Alpha, which was volume fraction, it's a dimensionless quantity, so everything is 0. Now you see, after that we have internal field. So internally within the domain we need to specify what is the value of alpha. So we have written uniform 0. It means everywhere within the domain we are giving value of alpha to be 0. So it means we are specifying everywhere air, because this is alpha for water. Then we have boundary field. We have defined for left wall type as 0 gradient. What it means, 0 gradient is nothing but a Newman type boundary condition for the volume fraction field. So it is gradient of alpha in normal to plane is equal to 0. So that is a Newman type boundary condition for alpha. Is this point clear? Then right wall again 0 gradient, Newman type boundary condition. Lower wall 0 gradient. Then we have atmosphere. Atmosphere is having type inlet, outlet. So it means anything can come inside, anything can go outside. So mathematically if you see, this boundary condition is actually linked to the pressure and velocity field. So mathematically it is linked to pressure and velocity field. If pressure or velocities are normal to the outward direction, then things will be going out. If it is in inward direction, then things will be coming in. And below that you have one value, inlet value. What it means that when this inlet outlet boundary condition will be working, if anything which can come from outside is actually only air. So typically if you have an open tank and water column inside, then outside will be atmospheric air only. Because of the splash, water can go outside, but from outside water cannot come inside. So that's why outside only air can come inside. So inlet value will be always 0 only. And what is the initial value? So below that one more term is there, value 0. What it means, at time t is equal to 0, which phase is present at that boundary. So at time t is equal to 0, air is present there, so that's why 0 is written. Is this point clear? And other than that, if you see the default faces are front and back. I need not to solve equation there, so that's why their value is empty. All are clear with this? So this is the boundary condition for alpha field. Now you see velocity field. What is the dimension? First is mass, mLT. So, m will be 0, length has to be 1 and time has to be -1. So, 1 and -1. Rest everything is 0. Is this point clear? All are clear with this point? Then internal field. What should be the value of velocity for all the internal cells? Velocity is a vector quantity. We need to specify its three components u, v and w. So, that is why we are writing 0, 0 and 0. Is this point clear? Then we have boundary fields. Left wall type is no slip. We are doing a macroscopic flow situation where there is no slip present at the wall. So, no slip means velocity in tangential direction is equal to 0. Then we have right wall, again no slip boundary condition, lower wall again no slip boundary condition. What about atmosphere at the top? At the top, the value of velocity should be governed by the pressure. Okay, so whether if pressure gradient is favorable, flow will go outside. If it is adverse, flow will come inside. So, once pressure is calculated, then gradient will be computed at the boundary nodes, and depending upon value of pressure, flow can come inside or outside. And presently, at present, what should be the value of velocity for the top boundary nodes? That should be 0, 0, 0. All the three components are 0. So, initially there is no disturbance at the top of the tank. And default phases again we need to keep empty. Let us see the third file, which is pressure file. What is the unit of pressure? kg per meter in fundamental dimensions per second square. So, that is why 1 minus 1 minus 2. Okay. So, value of pressure in all the internal cells 0. Left wall is having fixed flux pressure, and what is the meaning of fixed flux pressure? Again, fixed flux pressure is identical to that of Newman type boundary condition for the pressure. That gradient of pressure in normal direction at the boundary is defined equal to 0. Or in other sense, if you see typically, whenever at a particular, because pressure and velocity are two coupled quantities. So, if pressure and velocity are two coupled quantities, if you specify the value of velocity at a particular point, then pressure should be computed based on the data of the velocity. If you know pressure, then velocity should be adjusted to the given pressure situation. So, once we specified no slip condition, we have defined the value of velocity at that point. So, that is why now pressure, when it will be computed based on the discretized set of equations. So, what we are simply telling that at boundary node and just in the internal node, pressure will be coming from the computations from the within the domain. Okay. And other than that, if you see, we have written below uniform 0. What it means? At t equal to 0, value of pressure at that boundary is actually 0. Similarly, because all other types are also wall, so everywhere we are defining equal to 0. Then for atmosphere, we are using total pressure boundary condition. So, total pressure will be actually kinetic and dynamic head, and that we are defining equal to 0. And other default phase is again empty. Is this point clear? So, maybe to understand this exactly how the pressure and velocity boundaries work, if we go further details of the discretization of boundary cells, then we may understand this point more better. So, all the files are done. Now, what you can do, again you can open ParaView and you can load the files the way you the way you loaded earlier. इसमें वो दिखाना है, ये नहीं, वो वैल्यू कहाँ आएगी अल्फा वेरिएबल्स की,
सर वो सेट फील्ड्स चलाएंगे ना तब।
उसके बाद आएगी. ओके. Okay, maybe you need not to open the paraview now. So just you understand one point, what we have done at the moment. At the moment, everywhere we have defined value of volume fraction field to be 0. But what we need to do? We need to tell our domain that some portion of the domain should have initial water column. So I need to now initialize the water column. So to initialize water column, what I will do, I will go to system folder, and in the system folder I will be using file set fields dict. If you open this file, you will be finding first line is written as default field values, and there it is written volume scalar fields alpha dot water 0. So it means default value of alpha in entire domain we are specifying to be 0. Then important point you have to note down, I have written volume scalar field. If I need to define the velocity, then I will be writing here volume vector field. Okay, and instead of specifying a single 0, I will be putting a bracket and I will be writing x, y and z components. Then below that I have one more command which is now specifying the regions. So regions command typically is used to specify where we need to define the value of the variable. So what type of region we are using? We are using box to cell command. Okay, and in box to cell command we have defined a box which is having actually two set of vertices. So one point is 0 0 minus 1. 0 0 minus 1 means somewhere in the negative z direction, and other point is 0.146, 0.921 and 1. So means somewhere over here. So basically what are these 2 points? These are the diagonally opposite points of a box. These are nothing but the diagonally opposite points of a box. So if you have defined this point and this point, you can create a box in between these 2 points using the box to cell command. So simply I will be getting some box like this over here. This type of box I will be getting, okay, because I specified the diagonally opposite points, this point and this point. One thing you need to keep in mind, our z was varying only from 0 to 1. They have written here from minus 1 to 1. So basically they are covering the entire portion in the z direction. Okay, and what should be the value of volume scalar field inside this? It should be 1, because their value of alpha should be water. Okay, so after we can now close this file, we can again go to the terminal. So if you have kept your terminal,
जीरो फोल्डर में जाना पड़ेगा, उसके बाद सर ये वाला है, उसके बाद अल्फा डॉट वाटर का रीनेम करके बनाना पड़ेगा.
ठीक है, हाँ ठीक, अभी सेट फील्ड से वो खुद ही रीनेम हो जाएगा, नहीं हो रहा है. Okay, now go to the terminal. Do you have earlier terminal open? Please type command set fields. SET will be small, F capital, then everything else will be small. Have you typed the command set fields? You read something is written in the terminal. It is written that a box has been specified with some coordinates within which the value of internal volume field has been specified. Is this point clear? After running this command, if you go to 0 folder, rewrite नहीं हुआ था, बट कुछ उसके नीचे भी कुछ नहीं आया, कुछ तो आया होगा ना नीचे, तो हाँ डिलीट करके दोबारा रन करो. ठीक है, जाओ, हाँ आ गया ना खुद. So now you can see that in the 0 folder one new file is generated which is alpha water. If you can open this file, you can read that some of the values will be 0, 0, 0, some of the values will be 1, 1, 1. Can you open this file? Alpha.water. Maybe it may be heavy for some of the machines, but if you are able to open it, you need not to open. You will be finding that in this file, you will be getting all zeros and ones. Okay. After this, please go to ParaView. In the same terminal, please type ParaView. ParaView or ParaFoam? ParaView से आ जाएगा. नहीं आ रहा है ना, पैराफॉर्म टाइप करना पड़ेगा सर. अच्छा फिर स्किप 0 टाइम. हाँ
skip 0 time confirm.
So all of you have opened again the file in ParaView using OpenFOAM loader. Now in the left side you will be finding one option, skip 0 time. Is there a checkbox, skip 0 time? Are you able to find it? Please uncheck it and click on apply. Uncheck it and click on apply. Please uncheck and click on apply. Have you done? After that, you can now go to, there is in the top written solid color. All of you are able to see solid color? इसमें आया कि नहीं?
वही ये रनिंग हैंग हो.
अच्छा आना चाहिए था ना अल्फा डॉट.
ये चीज़ आनी चाहिए.
हाँ तो बंद कर दो इसको भी, इसको फाइल को बंद कर दो. Below the solid color, you will be finding different variables are listed. Alpha, velocity, pressure. Please click on alpha. हाँ स्किप 0 टाइम किया आपने.
हाँ किया, ये वाला यहाँ पे ये टर्मिनल यहाँ से कुछ कर दे.
OpenFOAM reader.
now
गलत आ रहा है, ये 1 आना चाहिए था.
ये अल्फा डॉट वाटर में जब से फीचर हो रहा है तो वो एस्क में नहीं आ रहा.
हाँ
कोड बना रहा है.
we'll run then let's see. Yeah, no issue. So no issue if you have gone to alpha dot water, so it would have shown you a column of water. Probably it is not showing for the 0th file. Let us run the code and then let's see. Okay, so up to this point all are clear, but you have seen that when we have run the set field command, it has created a file alpha dot water. Once it created file alpha dot water, it means it has specified where alpha has to be 0, where alpha has to be 1. Now let's see further, because we have approached the lunch time, so I'll be quickly showing you all other steps also. Now you can see another thing, we can go to constant folder. In the constant folder there is this file. One important thing you can see in the constant folder, are you able to get polymesh folder? Within the constant polymesh is coming. So earlier if you see, when we opened the constant folder there was no polymesh, but now there is a polymesh folder. It means once we created the mesh, all the mesh information is now saved inside this polymesh. And why it is being stored in the constant folder? Because we are using the Eulerian grid and this data will be remaining fixed for the entire simulation. Now you can open G. Please open G file. All of you please quickly open now, be little fast. Now you are all are habitual with the file format. So if you open G file, unit of G should be LT minus 2. We have written 1 minus 2. The value of G we have to specify in y direction, negative y direction, value is minus 9.81. Please let's open the next file. Next file is our transport properties. If I open the transport properties file, you can see we have phases, water, air. We need to put in the same sequence, primary first, then secondary. And first water is having transport model Newtonian, because non-Newtonian we can also use in OpenFOAM. So we are using Newtonian. We are defining its density as 1000 and nu, which is kinematic viscosity as 1 into 10 to power minus 6. Please remember this, in OpenFOAM nu is actually kinematic viscosity, it's not the dynamic viscosity. And then other two properties for air are density is 1 and kinematic viscosity is 1.48 into 10 to power minus 5. Sigma is surface tension coefficient, because in addition in the momentum equation we need to solve surface tension force term. So that's why we are giving coefficient of surface tension as 0.07. And if you go to turbulent properties, please go to turbulent properties. What is written simulation type? So if you choose any of the turbulent models, for example K epsilon or K omega, then we need to specify the values of turbulent kinetic energies and different model constants. So presently we are not using that. That is done. Now let's go to system folder. In system folder, let's first open the FV schemes file. We will not do any modification, but you can see in our equation we have different terms, divergence of rho phi u. For that we are using Gauss linear upwind scheme. For divergence of phi alpha we are using Van Leer upwind scheme. So like we are specifying all these schemes. Probably unless or until you have knowledge of theory of the CFD, you will not be able to understand what are these terms, but these are specific to the different CFD schemes which we use. Let's close this file. Let's quickly see the FV solution as well. So if you see the FV solution, then you can see that we are specifying tolerances for each and every variable. For example, the tolerance for alpha equation is 10 to power minus 8, tolerance for pressure correction equation is 10 to power minus 5, 10 to power minus 7. So likewise, velocity equation 1 into 10 to power minus 6, how many number of which type of method we have to use. So all these things we can actually specify in the FV solutions file. After this, we can go to one important file. Now we need to tell our solver that for how many time steps we need to run the simulation and what should be the different control parameters. For that I will be going to control dict. let's open the control dict file. If I open the control dict file, application is Interform, we are using Interform solver. The first option is start from means start time. So, and start time value is written 0. So, it may so happen that in certain cases, if partly I have run some simulations and then say system has crashed or there was some power off, and I have some intermediate file, and from that point I need to start. Then instead of start time, I can write their latest time, and automatically it will be starting the simulation from whatever the intermediate latest file we are having present. And then next option is stop at. So we will be stopping at end time, and end time is 1. So after 1 second, we will be stopping. We need to specify delta t. What will be our time step? So time step I am specifying as 0.001. Then I need to specify write control, whether my write control is adjustable runtime or not. So for example, it may so happen that I have given a fixed time step of 0.01 and I need to store data at 0.0015. Then time step may have to calculate for that particular instant, and then only it can actually save the data. For that we can use the adjustable runtime option. And then I have write interval 0.05. What it means? It means that I will be storing data after every 0.05 seconds. Then I have purge write 0. If I make purge write 1, then only it will be keeping the latest file, and once a new file is generated, it will be removing the previous file. So typically, if say sometimes the CFD schemes give advantage of running a transient simulation, so running a steady state simulation in a transient manner. So if say I am interested only in the last final stage of the solution, then I may use this option. And write format is binary, precision is 6. And then write compression means if you want to reduce the size of the file, if you want to compress this file, that we are keeping as off. Sometimes if say we do not have memory, then we can compress and then later on expand the files. And then we have time format, we are keeping general, time precision is 6. Now one important point, runtime modifiable. Runtime modifiable option, if runtime modifiable and adjust time step option are yes, it means that during the simulation, depending upon the value of different current number, which are considered as stability criteria for explicit time integration schemes, we can actually modify the value of the time step. If we make this option no, then time step will be remaining fixed throughout. Now, we are giving maximum value of current number. So, current number we will be having now two equation. One is momentum equation. For that maximum current number is 1. In addition, we are also solving the advection of volume fraction. So, for advection of volume fraction, I am writing maximum alpha current number. We do not maintain alpha current number more than 1, because whenever solution will be marching, interface can at max travel from one cell to another cell with a single cell distance. If we are jumping interface with cell jump of more than 1, then errors in interface reconstruction and volume fraction advection will be huge and we will not be getting correct results. So, it is always kept 1, and for majority of the momentum equations also it is kept 1. However, depending upon the situation, sometimes global current number can be kept even larger than 1 for momentum equation. And then we have maximum delta T1. So, whenever I will be using the adjustable time step option, it may so happen that my actual current number is so small that based on the limit of the current number, time step is coming to be a huge number. So, that number we are limiting by value 1 over here, that though it should calculate based on CFL number, but it should not jump out of this bound. So, this is all about write control. Now, what you can do, you can close this, again open the terminal, and in the terminal you can click on, you can put the command interfoam, INTER capital FOAM. Before putting the interform command, if you are again using the new terminal, you have to write OF7. So is it running? Finished. So maybe again you can open ParaView and you can visualize your results. आ गया, आ गया. हाँ, ठीक है. So if you opened the ParaView, if you open ParaView from the top, in place of P variable which it is showing, you can select variable alpha. You can select variable alpha. Have you selected variable alpha? And now you click on run button from the top. So if you click on run button from the top, you can see how interface is advecting. Of course, grid is not good, so we are not able to resolve it properly. All of you are able to do it? You can even open surface with mesh, you can even check contours for velocity, you can check contour for pressure. So maybe I think all of you are able to run. So with this we have only seen that what are the basic idea of the interform solver and how we can run a simulation, how we can set up a simulation in interform and how we can run that simulation. If we have to do any new case using this solver, it is always advised that we should select the closest case and then we modify the case files, because writing each and every file from scratch is not advisable idea. We will be doing lot of mistakes in putting various colons or commas or brackets. So better way is we can take the closest file and we can modify that. Likewise, I will discuss in the last session, which is on Friday. One more laboratory session is there on OpenFOAM. In that session, we will try to modify this file for an axisymmetric bubble rise case, where we have specified an air bubble in water, and when we will be doing this axisymmetric case, finally we will be getting our output something like this. Maybe this video is not running, so we can get that there is a bubble, how it is rising, and then we can also calculate its average velocity or centroid velocity with time, how it is actually rising. Okay. So with this, I think you can go for lunch. Probably at 2:30 you can again join for the next session, and that will be, next session will be in the same class.